Realistically rendering human faces is an essential task in creating digital humans in several of today's applications of computer vision and graphics, especially in the entertainment industry. To create such digital characters, it is common practice to 3D scan real humans using photogrammetry to digitally capture the facial geometry using multiple cameras in a studio setting. Facial appearance capture techniques go beyond capturing just 3D geometry and also estimate intrinsic reflectance properties of skin, such as diffuse and specular albedo, which capture skin pigmentation and oiliness. Finally, high-detail surface normals are often also computed as a byproduct of this process. Appearance capture is often formulated as an inverse rendering problem, in which the appearance maps are iteratively optimized and the face is rendered repeatedly until the result closely matches the real face seen by each camera. This optimization is done by simulating light transport according to predefined models of incoming lighting and skin reflectance. Typically, skin reflectance is modeled using two layers for surface and subsurface reflectance, that is, specular and diffuse reflectance. These layers are modulated by albedo maps, leading to the final rendered pixel. This analysis by synthesis process is supervised by real reference images. In today's systems, polarized light and cross-polarized cameras are also often used, helping to better separate diffuse from specular reflectance. In this paper, we revisit the simplifying assumptions made by state-of-the-art algorithms when making this challenging problem more tractable. First, light sources are often assumed to be distant, so that the omnidirectional distribution of incoming light can be more easily measured at a single 3D location by taking an image of a mirror sphere. Second, polarized light is used for better diffuse specular separation, but the light transport simulation still uses the formulation for unpolarized light. Finally, the simulation often only accounts for light coming directly from the sources, ignoring indirect bounces on the face itself, which cause the albedo maps to overshoot and compensate for the missing light. In this work, we depart from these idealized conditions and move in the opposite direction to demonstrate the benefit of using more realistic models of light transport. We show gains in the quality of estimated appearance maps as well as in the resulting face rendering, with only a small increase in computational complexity. We begin by looking at the assumptions of distant lighting. Face capture studios often do have near light sources, therefore breaking this first assumption. Here we use the method recently proposed by Riviere and colleagues as the baseline algorithm for our investigations. Our capture setup is inspired by the one in Riviere and colleagues, but it has also some differences, mainly in the size and number of light sources. As in the baseline method, our 12 cameras are similarly arranged into 4 triplets and our lighting is horizontally polarized. Our 16 pairs of LED bars are located about 1 meter away from the captured face. Each camera triplet includes a narrow baseline stereo pair and a third camera that is cross-polarized relative to the lighting. That is, this third camera is mounted with a polarization filter that attenuates specular highlights, letting mostly diffuse reflection pass through. We now depart from the baseline system and drop the assumption of distant lighting. It's easy to see when a point light source is near the face, the direction of incoming light varies significantly across the face. Therefore, we propose to compute the 3D positions and orientations of our light sources explicitly. To calibrate the 3D positions of the light, we capture a mirror sphere, annotate the vertices of the LED bars on the captured image, shoot rays from the camera, and reflect on the mirror sphere. We do the same for more camera views. The corresponding 3D point is then determined by minimizing the sum of distance to all the reflected rays. After we obtain all 4 vertices, we can then fit an optimal rectangle. We also constrain the edge length to the measured values. We then sample points on the rectangle, represent them as point light sources, calibrate their intensities using the HDRI of the mirror sphere, also compensating for the attenuation on their intensities that are inversely proportional to their squared distance. Here we see 4 real images taken of a mirror sphere, showing the reflections of the light sources as seen by 4 different cameras. Capturing such images is already a common practice for building an environment map when assuming distant lighting. As such, our calibration method introduces no additional requirements for data capture. To demonstrate the quality of lighting calibration, we reproject the estimated lighting directions onto the image plane and overlay on the real images of the captured mirror sphere. Here we see the result of the sparse environment map computed by the baseline method. Note how the model makes poor use of the allowed resolution for the environment map by using lighting directions that are not sampled on the actual LED bars. Here we see that our calibration aligns much better with the underlying image of the LED bars. This is observed in all camera views used for inverse rendering and not only on the main frontal view. Our calibrated 3D lights actually allow us to generate a different environment map for each point on the face to compute more accurate appearance maps and renders. On the right, the variability in lighting across the face clearly shows that the distant lighting assumption and the single environment map yields a poor lighting model when light sources are near the face. The benefit of having more accurate calibration of lighting is evident when rendering the face under harsh lighting that produces stronger shadow lines. Here we see two copies of the same reference image depict the face under the illumination from a single pair of LED bars, shown on the bottom left. And now we see the corresponding face rendered by the original baseline method and with our new calibration, showing more accurate shadow lines. Here we see a similar example of a second face under lighting from a different pair of LED bars. And one more example. Now we also show the benefit of more accurately calibrating the intensity of each LED bar, which can be done automatically using the reference image and inverse rendering optimization. The baseline render is computed using an environment map whose intensities are taken directly from an image of the mirror sphere without further optimization. As a result, we see here that the per pixel rendering error of both methods, showing that our new calibration method provides more accurate rendering. While the white areas indicate imperceptible error, blue tones indicate the render is too dark, and the red tones show where the render is too bright. Here we see a similar example under lighting from a different pair of LED bars. Optimizing the intensity of light coming from each LED bar once again helps to significantly reduce rendering error. And one more example with a different face, camera, and lighting direction. We now move on to revise the second simplification found in state-of-the-art methods that capture the face under polarized light without explicitly modeling polarized light transport. When the camera is cross-polarized with respect to the light, the captured face is often assumed to be perfectly diffuse. Thus, one can directly fit a diffuse albedo to the cross-polarized imagery and estimate specular albedo once the diffuse component is known. However, perfect diffuse specular separation assumption does not hold in general multi-view setups, and there's remaining specular signal in the cross-polarized imagery. In our setup, we observe degradation in diffuse specular separation, especially for the camera that views the face from below, which is evident from the specular reflections in the eyes. We instead model polarization with Stokes vectors and Mueller matrices explicitly in our renderer. The four-dimensional Stokes vector described the polarization state of the light. The entries correspond to the intensity, the horizontal vertical component, the diagonal component, and the circular component. Mueller matrices describe the change of polarization state as transformation applied on the Stokes vector. We model the horizontal polarizers in front of the light and the vertical polarizers in front of the cameras for cross-polarized images, also the specular reflection on the face. We first compare against the inverse rendering result of the baseline method, which estimate the appearance maps using constant, smooth lighting from all LEDs turned on. Although the renders look similar, we again see improvements in rendering error, especially for our camera viewpoints located below the LED bars, for which cross-polarization is less effective. On the right, we also see that the computed specular albedo map also looks more homogeneous with fewer artifacts. And we also see that the facial appearance rendered by our new method with polarized light transport generalize better to novel lighting conditions. And similarly for another lighting direction. Finally, we address the third common simplification in inverse rendering methods for facial appearance capture, which corresponds to ignoring indirect bounces of light on the surface of the skin. Inverse rendering optimization for facial appearance often operates efficiently in texture space, such that the camera visibility and light visibility can be pre-computed, and no ray mesh intersection or texture lookup is needed during the optimization. Our indirect illumination technique follows this main framework to minimize the computation cost. For each point on the face, we pre-compute the samples and store their UV coordinates. These samples remain fixed during the optimization, and the indirect lighting component evolves as the albedos and displacement parameters update through the optimization iterations. As a result, the estimated albedo map becomes free of artifacts that are seen on the baseline results, where the albedo values overshoot near face concavities to compensate for the missing indirect lighting. We also found that in face concavities such as eye sockets, side of the nose, and along closed lips, the specular albedo values cannot be recovered using only direct lighting, since no direct specular reflections is seen on these areas. Simulating indirect bounces of light in these face concavities once again helps improve results, this time by adding new constraints on specular albedo. There are still some black areas in the specular intensity map shown here, which is because we don't have much light from above, behind, or from side of the subject. Using more complete spherical illumination would create more constraints for specular albedo estimation. These improvements in the appearance maps are a result of corresponding improvements in rendering accuracy, where the indirect light bounces of light that are missing in the baseline method are now accounted for and help guide inverse rendering with new method. And similarly for this second viewpoint and lighting direction. Finally, as with any Monte Carlo-based method, our method for simulating indirect lighting can produce noise renders if few samples are used. Fortunately, we found that the texture space subsurface scattering techniques implemented in the baseline method blurs away noise to provide smoother renders. In summary, this paper demonstrates the impact on inverse rendering quality when departing from simple, idealized conditions towards more realistic lighting models. Our departure point is a state-of-the-art face capture system, and we demonstrate several improvements to its lighting models. To avoid largely increasing the computational complexity, we propose enhancements that are specially tailored for this inverse rendering task, while showing gains in the quality of the facial appearance maps and rendering accuracy. Thanks for watching.